we just had the test, homework 1, oh my goodness. Homework 2, task 1 deadline. Hopefully we're feeling okay with that. It looks pretty bad on my end, the overall results. So if anybody has questions about it, I'll dedicate a little bit of lecture time to talking about it. I think overall, those of you who started early enough did well enough, but a surprising amount of the class started really late, which is telling me you're all getting kind of exhausted and worn down. Is it 12:42? Is there no flash photography? If my camera doesn't have ROM. Was somebody taking pictures with flash photography a minute ago? Yeah.
For this project, do you have 30?
Probably. That sounds right. It's on the course schedule, though.
Oh, is that ever the last project has to do the same day as project?
The application objective will be on the deadline of task 3 for each project. On the actual deadline, not the expected deadline. So on the task 3 actual deadline, the red scary one, that'll be the application objective for each project. Which I realize does create a little bit of conflict in your time management. Which one do you prioritize? Even if you got the deadline for task 3, do you work on the expected deadline of task 1? I think a lot of people put off task 1 of project 2 because they were working on the application deadline. It's something I want to rethink about the schedule next semester, but for this semester, that's the way we're going to have it. And the idea is if you are able to earn the application objective, like that's where you're really working towards your A. So to get an application objective, you need enough flex time in your schedule after getting the task done to add that application objective on there. So I'm not mad at it, but I think there's something we can do a little better there, a little bit of tweaking on the deadlines. For those of you who did not meet the task 1 deadline this morning, it'll be like either tonight or at the latest tomorrow morning if I collapse tonight. I'm going to try to get it all done tonight. You'll get your deadline extensions. I'll send out an email saying you got an extension. I'll give you the extension in Autolab, and you'll use a recovery opportunity. So if you didn't meet that deadline, right now Autolab isn't accepting submissions until I have to manually add in all the deadline extensions. It takes a while. I have to add in about 100 of them for what it's worth if anybody's wondering about the stats of the class. About 300 students. There are 403 students across the 4 sections. 300 students, I think 301, met that deadline, like a scary deadline. I don't like seeing that number so bad, but the scary deadline. Only 301 of you are not using a recovery opportunity on that one. So it is what it is. A good number of those 100 students who didn't meet that deadline have already resigned for what it's worth. And they're already done with the course, but I mean, it is what it is. That's part of 116, unfortunately. In task 1, I'll defend it. Task 1 isn't that hard necessarily. You are learning classes for the first time, so in that sense, it's hard. You're learning a new concept, but it is pretty tedious and time-consuming. Like there's a lot. Just reading all of the text. There's 2 pages of text, so just getting through all of that is a lot. So I understand. And I think a lot of students just waited. You're getting kind of worn down. It's that time of the semester. I'm worn down too, and just didn't start early enough to get that deadline. I think that's what happened with most of the students who didn't get it done. Yes?
So my question is for you can get extensions on like the deadlines for tasks. Can you get an extension on the application objective?
No. Okay. So no extensions on the application objectives. And I actually got that question recently, so I updated the syllabus. I tried to never update the syllabus, but in this case I had to. Goodness, where is it? Right here. No recovery opportunities after the extension. So I did add that after the fact. But this bullet point, I'll defend it. This bullet point I think takes care of it, that it'll be used automatically because the alternative is failing. For application objectives, the alternative isn't failing. So implicitly it was there, but I made sure it was explicit. Good question, though, because I want to make sure that's clarified. The grading structure is different in this course than probably any other course you've taken, so I want to make sure everything about the grading is clear. So any questions about grading especially, I want to get those answers out there. Can you post project 3 before spring break? Yes. So I'll always post the project before the content for that project starts. So by Monday the 14th. Before this, I'm going to post Project 3. So within the next 5 days. It'll probably be Sunday night, not going to lie. It'll probably be Sunday night. Posting a project is one of those things where I always want to, even after it's done, I want to revise it and make sure it's as good as it can be before being released. So I'll be constantly revising it up until the point where I got to release it to y'all. But it'll be, if you've heard of it from previous semesters, it'll be the genetic algorithm assignment, but I think I might downplay the genetic algorithm side of it significantly this time. Yeah, and the code, you can find the code for the starter code of each project in my repos, but it will change for this semester. I'll update the repo, yeah.
For LO3, are we going to be going over concurrency?
Are we going to what for
We're
LO3?
going to be going over concurrency.
No concurrency. Oh, did I leave that on there? No, this should be gone. I was supposed to delete that. I'll have to update that. Concurrency, up until last semester, we covered concurrency as part of LO3. This semester, finally done with it. It's a confusing topic, and there's a lot in this class already. We finally got to cut that content. Concurrency is it's a beast. It's if you think anything we're doing now is hard, concurrency is like 10 times that. Concurrency is where you can have multiple pieces of code running simultaneously, and that just it's a whole new level of thinking. You have to really. It takes a while just to get your brain to wrap around that idea, and then have multiple pieces of code communicating to each other and working in sync to get a program to do what you want it to do. It's a lot. If you go to my GitHub, the GitHub where the projects and the examples repo is hosted, go to that repo and search go to that my GitHub and search repositories for genetic algorithm, and genetic algorithm will have the starter code if you're really eager to jump onto Project 3. Yeah, we're not going to learn concurrency. Concurrency is being pushed off to 220. You will learn concurrency in 220. That's right, Vlad. Concurrency is an important thing. I'll talk about it since it's not part of the course anymore. I'll take a little bit of time to talk about it. The slides, I think I can get through the slides in like 40 minutes today is the time, so we can take a little bit of time right here. We actually are using concurrency right now in 116, but I'm not asking you to code any concurrency. So for example, you run your GUI for project 2, and the user can click on those buttons, and at the same time, your program is processing those button clicks. So for example, if somebody were to click really fast and click a button twice, like click, and then click like less than a millisecond later, on that second click, your code is still processing the first click. But since the code is concurrent, it can still process that second click, even though your code's not done processing the first click yet. And your code is still displaying things to the screen while listening for those button clicks. You have multiple things happening simultaneously right now as part of the GUI. And then concurrency was explaining to you how to actually set that up and how to build programs that way. And yeah, like I said, it's a fairly intense topic. Concurrency used to be 3 weeks of the course, and then we had to cover OOP and FP so much faster to make room for it, and it's too much. What's the exchange rate for concurrency? 0. You don't get your money back. Not in 116 anyway. It's a good topic for later in your career. 116, we thought a lot of us got together and decided it belongs in 116, and we were wrong. It's a very interesting, very important topic. So, for example, probably every single one of your laptops and phones has multi-core processors. We want to be able to take advantage of those cores. If you're writing single-threaded, non-concurrent programs, you're only using one core at a time. So the other cores might be able to use by other processes, but if you want one program that can take full advantage of that, of all those cores, or if you're running a GPU and you got like thousands of cores, you want to be able to take advantage of all the power. You don't want to be saying, hey, GPU that I spent thousands, hundreds at least of dollars on, I want to use one of your thousands of cores. That program's going to suck. So we need concurrency. It's just kind of a fact of life for programmers these days. We need concurrency. We need to take advantage of that hardware that we have. For other reasons too, like the GUI. A GUI doesn't really exist if it can only do one thing at a time. Web apps don't really exist if your web server can only serve one user at a time. It's not a very interesting website. If you have to join a queue, you go to your favorite website and it says, you're number 1 million in the queue, wait your turn. That's not fun either. Everything's concurrent these days. So it is a very important topic. Just 116 is a little too early to introduce it, unfortunately. For any evidence of that, just see what I talked about with task 1 of homework 2. Even that's crushing people. We're just creating a few objects and testing them. Throw concurrency in there. We were optimistic. I thought that we could get it, and it's just too much. Nicholas. Yeah, if you go over the memory diagrams, I would say it wouldn't be sufficient to go over the memory diagrams of examples in class to prep for the quiz. I'd say that would be necessary, but not necessarily sufficient, that you should study something else too. If you just memorize the examples in lecture, that probably won't do it on the quiz. The quiz, you're going to get a program you've never seen before, and then you have to sketch out the memory diagram of it. So if you're only studying off of an example where you already have the answer right there for you, it just might not be quite enough to study for that quiz. Yeah.
Did you do memory diagrams like this last semester?
Not with this syntax. I still showed what was happening in stack and heap memory, but I did downplay it a little bit, and we didn't require it on the quizzes. On the quizzes, I would just open-endedly ask, trace through the execution of this program and tell me what happens on the stack and heap. This semester is the first time where we're formalizing that into here is how we're going to do memory diagrams in this class, and then on the quiz, do memory diagrams in the way that we showed you. So it's the first time we're formalizing it, but that content was always part of the course. And it was hell to grade those quizzes. We just get paragraphs and have to parse through it and figure out if you know what you're talking about or not. And now we just look at the memory diagram, we can tell. Ren. All right, once Ren's in chat, things devolve. Let's go over some slides. All right, so today we want to talk about the state pattern. There are shouldn't say multitudes, like 10-ish design patterns that are approaches to common problems and solutions to those problems using OOP. So using polymorphism and inheritance to try to solve some common problems. There are quite a few of these, 10-ish or so. If you're interested in them, check out the Gang of Four. That's the 4 people who got together and came up with these things over like a weekend or something. They were all, I believe they were all consultants, and they've seen all kinds of software and all kinds of different companies, and they all came together and said, hey, we constantly see people apply this pattern to this problem. Let's give that pattern a name and then publish it. And then they shared all these design patterns with us. So we can see like the common approaches people are taking out there in industry to solve certain problems. We're going to talk about the state pattern, but there are many other ones that you can study. We're just not going to talk about them in this class. The visitor pattern, factory pattern, they're just a whole bunch of them. The state pattern is the one that we're going to talk about. And this is going to be an application of polymorphism. And I can't stress this enough. The state pattern isn't, I mentioned this last time, but the state pattern isn't necessarily something I like deeply care that you learn. As strange as that's going to sound, devoting 2 lectures to it and having task 3, the project, devoted to it. It's not something I necessarily care that you learn. If you walk out of this class not fully understanding the state pattern specifically, I'm all right with that. What the state pattern is, and the reason we're talking about it, is because it's an application of inheritance and polymorphism. You need to use both of those in a unique way to be able to get the state pattern to work. So as you're using the state pattern, what I do care about is that you're getting practice with inheritance and polymorphism. You have to use both of those concepts to enable use of the state pattern. And then you're going to reinforce those topics, that you're going to have the state of the object, which is going to depend on, it's on my next slide, I'm trying to point to it. But the type of the state is going to change the behavior. It's going to make more sense later. But right now, if we want to change the behavior of an object, we're going to change the state of the object. We go to its state variables, we change the values in those state variables, then the behavior changes. We have a character in a game that has a jump height stored in an int, and that jump height is 5. We say we want this behavior of this player to be able to jump higher. We say jump height equals 12. Now that player can jump higher. We just change the behavior of that object. But what if we want to significantly change the behavior of the object? We don't just want the player to jump higher. We want the player to be able to double jump. We want completely different behavior. We want the player to be able to fly. We want the player to be able to use a jetpack. We want them to significantly change their behavior. How do we do that? Well, we're going to add some if statements, right? This is the way we would do it. And again, nothing wrong with if statements. They are banned on the homework specifically to prevent you from doing this, so you have to use the state pattern. But this is how we would usually do that. If some condition, if the player has a jetpack on, jetpack behavior, else jump behavior. And this is fine, but we're going to get to a point where we have a lot of else-if statements. What if we want 5 different behaviors from the same method, from the same action that someone takes? We're just going to say if behavior, else if some behavior, else if some behavior, else if some behavior, else some behavior. And this code is going to get very hard to maintain, very hard to test. If you're writing tests for this method, you have to make sure you write a test for every single path through this method. You're going to have one massive test case with just all kinds of crap going on. You're going to have hundreds of lines in a test case, which some of you will have anyway in some of your testing. I think I had like 1,000 lines of code to test test all of Project 2. But with this, you're going to be multiplying that by some factor, not necessarily 5, but you're going to have more complex tests. Hard to read, hard to maintain. And every time you add a new behavior, you want another else if in here, and condition 4, behavior 4. You have to go back to those tests and make sure they still work. Make sure you didn't break anything, because this else behavior is going to change it based on that else if. Now there are some conditions that aren't reaching your else anymore. You have to make sure you didn't break anything. You got to retest everything. It's a pain. So nothing necessarily wrong with the if statements, but it will get a little messy. No if and no var? Oh my goodness. No, we're not doing that, Trevor. But yeah, a little foreshadow to Project 3. Project 3 var is going to be banned. You'll be able to use your conditionals again. The only thing that's banned is var, but var will be banned. You can't have variables. And the reason for that is to force you to use recursion. Ban conditionals to force you to use OOP. Ban var to force you to use recursion and immutability, which are both topics of LO3. And functions, first-class functions. All right, so in comes the state pattern. We're going to get rid of those conditionals by, instead of having an object define its own behavior, we're going to defer the behavior to a state variable. The state variable is going to store an object, and whatever behavior that object has, that's going to be the behavior of the object that's calling the method. So instead of saying if some value do some behavior, instead we're going to just defer to an object, and depending on the type of the object, and this is where our inheritance and polymorphism will come in, depending on the type of that object, we're going to get different behavior. So we're going to have a state variable, which is going to be of the type of an abstract class, and we're going to store different child classes of that, different things that extend that state class that are going to have different behavior. And depending on what type is stored in that state variable, we're going to get different behavior. We're going to get the behavior of that particular state. This is my last slide of background and concepts. I know this is very fuzzy at this point. So we're in our abstract state class, we're going to define the methods, usually abstract, that need to exist in every state. All of the behavior that we're deferring to the state for, and that's what we're going to call our API. For the homework, your API is number pressed, enter pressed, loyalty card pressed, cash pressed, all the press buttons, all the buttons that can be pressed, and also display string and items in cart. That's your API. Those are all the methods that the checkout machine needs to have, and I should probably foreshadow that too and just be explicit about it. The state pattern will be applied in task 3 in your self-checkout class. Your self-checkout class is going to apply the state pattern in task 3. That's where you're really going to want some if statements. You're not going to have them, and you'll have to apply the state pattern. So that's your API. All the button press methods, display string, and items in cart, you can defer all of that to your state for that behavior. That's your API. Those are the methods that can be called that the state is going to be in control of. Then each state is going to define how those methods behave when you're in that state. And to change states, we create a new object and replace that state variable with the new object to change states. Any question? Ooh, we have a question in chat. Which one? What exactly is a loyalty card? Loyalty card, like, I guess if you haven't gone shopping, maybe this. Yeah, like a bonus card, though, where you scan your card, where you go to check out, like, basically anywhere, and they say, do you have your card? And then you say no or whatever, or you enter your phone number. That's the loyalty card. And then there are certain sales that you only get after you scan that card. That's the idea of the loyalty card for the application objective. Or if you say, no, I don't have one, and they say, do you want to sign up for one? And you fill out some paperwork, and they give you a card. That's the loyalty card. If you haven't gone shopping at all, it's a way that they can track you, basically. And they incentivize it. That is this purpose, if you didn't know that. It's a way that they can track you, and they incentivize you with sales. There will be certain things that are on sale only if you scan your card. And then once you scan your card, you get those sales. And then they track your card or your phone number, and then they'll send you targeted ads in the mail and say, hey, you should come over to our store and buy these things. Here's some coupons or whatever. It's pretty ingenious. Like that didn't exist, I guess, when I was born. I don't know, 20 years or so. Really, once computers started becoming a thing and the internet started becoming a thing, we saw those pop up in every store. I don't know if that's relevant to what we're talking about. Jesse, you're off track. That's a good way of summing it up. Are you part of our rewards program? That's what we're talking about here. I know, Trevor, I was going to use that. I was going to use CVS as an example, but CVS closed, so I can't use that as an example anymore. But that would have been my example. You go to CVS, they ask for your card. But that's the idea of the application objective. All right, let's get off of this slide. Okay, so what the hell does any of that mean? So that is the state pattern, by the way. Like that's technically, I covered the state pattern. Kind of like that one slide of polymorphism. I'm like, technically, I covered polymorphism. So there's no new concepts coming, but I would be willing to guess like at least 80% of you have no freaking clue what I just said and all that. So let's go into an example, and we'll re-explain all this stuff with a concrete example. And for that, I'm going to call in my good friend here, Bruce Banner, to help us out. So Bruce Banner, if you haven't met him, if you don't know him, he's a scientist. He's a world-class scientist. He's fictitious, in case anybody actually doesn't know who this is. Fictitious character. Scientist, he's able to drive a car for what it's worth, just like most people. And he's not very helpful in a fight. He really can't do much to help you. If you get in a fight and he's with you, he's probably running. But if you piss him off, he's going to become the Incredible Hulk. The Incredible Hulk has different properties. He's not a scientist by any means. He's not, can't really think, I don't know. He can smash cars. He can't drive them. He's just going to destroy a car. But he's freaking great in a fight. He's a little bit out of control. He's not going to be in the lab helping you with any science anytime soon. So what we have right here is one man, but two very different behaviors depending on his current state. That's what we want to talk about with the state pattern. He has two very different states, And let's take a look at some code and see how we're going to simulate a Bruce Banner. So we're going to create one Bruce Banner class, and he can be in these two different states. The state is going to determine his behavior, which can either be Dr. Banner or the Hulk. So when we set up the Bruce Banner class is going to be the person in either of these states. Bruce Banner can either be Dr. Banner or the Hulk, and when we set up this class to simulate a Bruce Banner, we're going to create a state object, and I'll show the rest of the code for these states as well. Seems like Jesse didn't watch Endgame. So we're going to create this variable named state, which is going to be the state that he's currently in. And I'm going to initialize that to an object of type Dr. Banner and pass a reference to himself to Dr. Banner. And we're going to see the Dr. Banner code in a bit. The important part here is that we have these methods. I'm going to say these are 4 methods that are going to define the behavior of Bruce Banner. We can make him angry, we can calm him down, he can use a car, and he can fight. He's going to have different behavior based on his state is going to be the big thing here. So with Dr. Banner, with Bruce Banner, we're going to defer all of that functionality to his state. We're going to say state, make angry, state.calm down, state.use car, state.fight. And then the state abstract class is going to say, if you extend me, if you want to be a state class that Bruce Banner can be in, you have to implement these 4 methods. And then Bruce Banner is just going to defer to his state to have different functionality for these 4 methods. So when he's Dr. Banner is going to extend state, and we're going to have a reference to Bruce Banner so each state knows the object to which it's attached to. That Dr. Banner, the state, is going to know that it's attached to this Bruce Banner. Technically, we can have multiple Bruce Banners in this because we can create, say, new Bruce Banner multiple times. We're just going to create one of them, though. So Dr. Banner is going to have a reference to Bruce and implement those 4 methods to define how he behaves when he's in the Dr. Banner state. So all right, I got ahead of my slide. I already said all that stuff. So for each state, never mind. I do want to talk about this more. Sorry about that. So for the Dr. Banner state, I'm going to ignore this and this for now. But in the Dr. Banner state, when you calm him down, I'm just printing things to the screen. Again, just like most of these lectures, I got to fit this stuff on the slide. So we're not actually doing too much here. We're just printing to the screen. He's already calm. We calmed him down. When he uses a car, I'm not showing the car class, but it's in the repo. The car class similarly doesn't really do anything interesting. I'm just using this as an example for the state pattern. But he's going to successfully drive this car. The false means he's not going to break that car at all. He's going to successfully drive it, and everything's fine. And in a fight, well, it's not going to happen too well. That's where we would implement the behavior, probably run away, hit the flight response. And he can also be in the Hulk state. Once he turns into the Hulk, you make him angry. Well, he's always angry as the Hulk. When he uses a car, he's just going to smash it. And when he's in a fight, he's also going to smash whatever's in his way. So very different behavior based on which state he's in. And then we just defer to the state. We have the state. It's currently Dr. Banner. We're going to get the Dr. Banner methods. Even though the variable is of type state, the object is of type Dr. Banner, and it's always the object that determines the functionality. And now we have these 2 methods that I skipped over. These are what we're going to call state transitions. Since Dr. Banner has a reference to the Bruce Banner object, and when we make him angry, when we make Dr. Banner angry, he's going to transition into the Hulk. This is what we call a state transition. We're going to take this reference to the Bruce Banner class, updated state, we're going to say banner.state. Oh, I don't have the Bruce Banner class here. Banner.state, this variable, instead of being a object of type Dr. Banner, we're going to replace that with a reference to an object of type the Hulk, and again pass the Banner class. So after you make Dr. Banner angry, his state is going to transition to the Hulk, and now after calling make angry, he's going to have all the Hulk behavior. If he's the Hulk and you calm him down, he's going to have another state transition back to the Dr. Banner state. So state transitions, very important. And our whole example looks like this. So we create a new Bruce Banner. He's in the Dr. Banner state. We call calm down. We're getting state.calmdown, which will be Dr. Banner. Already calm, no big deal. We call make angry. Dr. Banner's make angry. Banner.state is going to be equal to a new Hulk state. This is removed and replaced with the Hulk. On Friday, I'll do the memory diagram. For right now, I'll just go through it like this. He's going to become the Hulk. And now we call fight. We're going to get the Hulk behavior for fight. We call make angry. We get the Hulk behavior for make angry. So we can change the behavior based on these state transitions. We call calm down. We're going to switch back into the Dr. Banner state. Yeah, I almost said that too. We can create multiple Bruce Banners with the way the MCU is going now. So I guess we can leave the example like this. Yeah?
So you would make a Bruce Banner object, and any Bruce Banner object would have a state variable, and the state variable is what you're changing.
Yes. Yeah, so we create, so in our main method, when we want to use this code, we would say new Bruce Banner. And Bruce Banner is going to have a state variable on the heap. It'll have a state variable named state equal to an instance of Dr. Banner, a reference to a Dr. Banner. And then it'll defer to that instance for all of its behavior until it hits this state transition. Then we're going to create a new object on the heap of type Hulk. And then that will be the behavior from the state. This .state will then be an object of type Hulk, or the Hulk. And we'll get very different behavior after that state transition. I have seen that. Somebody named all their point of sale states after MCU characters. And they had way more than they needed. Yeah.
What exactly does abstract mean?
What exactly does what?
Abstract.
Abstract? It means we can't create an instance, like we can't say new state. This class only exists to be extended.
Also, would that be a parent class?
Yes. Yeah, so this is the parent class, and these are child classes. Or that's the super class, and these are concrete classes. I haven't been very consistent with that vocab, to be honest. Yeah.
So, if Bruce Banner turns into a Hulk, there's not a new object created?
So the way this is set up, we are actually creating a new object of type the Hulk. And then state is going to store a reference to that new object that was created. So technically, the way this is set up, if we say new Bruce Banner.makeangry, Bruce Banner.calmdown, Bruce Banner.makeangry, Bruce Banner.calmdown, we're going to get 4 objects on the heap. Okay. So it's a little awkward in that sense. We could avoid that, but it would just make things more complex. Yes?
So state would be the super class, and then Bruce Banner is your abstract class.
So Bruce Banner is a concrete class. That's just a straight up class like we would have done 2 weeks ago before we knew anything about inheritance. State is going to be the abstract class, and that state's whole purpose is to define the API. So the state is saying whenever Bruce Banner is in a state, that state is responsible for these 4 methods. And then Bruce Banner is going to take advantage of that and call those 4 methods, defer to the state for those 4 methods. So state, the variable, which is a state variable of type state, is going to only have access to methods that are defined in the state class. So we have to define these 4 methods, even though they're abstract, or not defined, but declare these 4 methods in the state class so we have access to them from a variable of type state. So that's the reason for the abstract class. And then we extend it to actually implement the behavior. Okay, in this state, this is the actual behavior. In this state, this is the actual behavior. Does that make sense? Good. How would you do it without if-else? Oh, I'm not part of that conversation. All right, any other questions on this? Oh, my watch isn't the right time. All right, so that's all well and good, but come on. We just did a lot more work than we would have if we just had a frickin' Boolean that said, if currently the Hulk, do this, else do this, right? We did more work. We created 3 extra classes that we didn't really need. This is just more work to get the same behavior as we needed before. Not helpful. But the true power comes in when we have more states, and the whole theme of this class is what happens when our projects get big. So from a small example, yeah, we don't see any benefit here. But when an example gets larger, that's where we're going to start seeing the benefit. So let me introduce you to Professor Hulk. This is a 3rd state that Bruce Banner can be in. He's in his Hulk form, but he has control. He can drive a car. He'll damage the suspension because he's pretty freaking big. But he can drive a car. He's great in a fight. He has a very different set of behaviors, a 3rd completely new set of behaviors for the same person. So when we want to add this to our simulation, to our program, we're going to create a new Professor Hulk class, extend state, and implement those 4 methods. That's it. If you were using if statements, this would get messy. You have to add an else if in all of your conditionals. You can't use a Boolean that says if the Hulk anymore. You have to have some variable that tracks which one of these 3 states you're in. It gets tougher. With the state pattern, you create a new class, extend the state, implement all of the behavior, and whenever you're implementing one of these methods, you're asking yourself one very narrow question. When Bruce Banner is Professor Hulk and someone makes him angry, what do you do? When you're using the state pattern, writing an individual method should be super easy, very easy. When I'm in the checkout state and somebody presses a number button, what should that press do? Should be a pretty straightforward question in any of the states. If they're checking out, if they already hit the checkout button, shouldn't do anything. If they're scanning items, it should do something. It should append to a string. Simple questions when you're implementing these methods, each individual method. You calm him down, yeah, whatever. When he uses a car, he can drive it, but he's going to damage the suspension. The Boolean, it only exists, you have to check out the repo to see that, but it just damages, it just prints out like cars damaged or suspensions damaged, whatever I put on there. And he can fight without being very destructive. He can control himself. So the methods are easier to write. It's setting up the state pattern that's going to be the challenge. This is probably one of the first programming tasks through 115, 116, where it's all about the design. Once you have a nice design for your state pattern and you have your setup, you're deferring to your state, you have your abstract class, and then you start extending that abstract class for each state. Once you have everything set up, actually writing the code for the method should be pretty easy. Little caveats, little tricky things here and there. But the bulk of the difficulty for task 3 is going to be setting things up. You're going to be creating multiple classes of your own design to be able to get the behavior and self-checkout that you need without using any conditionals. And it's going to be tricky to design, but easy to write the code. And that's kind of one of the trade-offs when you're using the state pattern. Tougher design, but easier to write the code. Whereas your career up until now is tough to write the code and almost zero design because everything's designed by the homework docs in 115 and 116 so far. And we have one extra switch. We have to add a state transition to be able to enter this state. And we're going to say if Bruce Banner, whether he's Dr. Banner or the Hulk, if he learns to control himself, at least in the MCU, we don't even know what state he was in when he learned control. But once he learns control, he's going to transition into Professor Hulk. And then once he's Professor Hulk, he can't get out of that state. He's going to stay in that state even though, well, with recent events, but so far all that's happened off screen, so I can't add it to my example. But anyway, he's going to learn control and then enter this new state. So we didn't change anything in our other states. We wrote that code, we tested it, everything's fine. We don't have to touch it again. And we just add a new state. It's very easy to add more states. You just implement the state and add the state transitions of how to get into that state. And you have more complex behavior very easily. You want to add 100 states to an object, 100 different states it can be in? It's not that big of a deal. Adding the 100th state is about as much work as adding the second state. So when your programs get large, it's easy to add more and more features without getting bogged down in all the details in an if-else block with 100 conditionals. Adding the 100th behavior is very difficult. Here, it's not a big deal with the state pattern. If you want behavior that's the same in every single state, don't defer to the state. It's perfectly valid. And if you want some default behavior, you can implement concrete methods in the state class. There's nothing stopping you from implementing methods in the state class and then only overriding them when you want to change that behavior in a particular state. So you have full control over your classes. You can use all the OOP, all the inheritance stuff that we've learned. Learn control happens in both states. Let's put it in Bruce Banner. Let's not bother putting it in each individual state. And when it comes to state patterns, this is something you'll hear in office hours if you don't have one. We like state diagrams. So it gets harder to look at the code and figure out what the code is doing at this point when we have these state diagrams, when we have the state pattern. So we like to draw these state diagrams, which are going to help us visualize what's going on. So we'll have each of our states. We have 3 different states Bruce Banner can be in. We have an initial state of Dr. Banner. And then depending on what methods are called, we're going to transition between these states. So if we call make angry on Dr. Banner, transitions to the Hulk. Calm down, transitions back to Dr. Banner. And in either state, call learn control, become Professor Hulk. And then there's no outgoing arrows from Professor Hulk. Once he becomes Professor Hulk, he's going to stay, at least in our simulation, he's going to stay Professor Hulk. So in office hours, you go, man, I have no idea what's going on here. One of my favorite questions is, show me your state diagram. And visualize, or at least verbalize what the idea of your states is, at the very least. Yeah?
But you would never want to make methods that are specific to, or like you would never want to make a method in like the Dr. Banner class. You would only want to overwrite the state.
No, you wouldn't want to implement anything in the Dr. Banner class or any of the states, the concrete states, unless it exists in the abstract method. The only exception to that would be if it's a helper method that's called from within that class itself. Then you might want to do that. It won't really be useful in this homework, but that's one case where you might want to. But you're never going to call those methods from outside of the class. They would just be internal to that class. From outside of the class, you're only going to call the methods that exist in this state abstract class. Yes?
What if I want to go from Professor Hulk to Bruce Banner?
Sorry, what was that? I got this
I want to
fan blowing
go
right.
from Professor Hulk to Bruce Banner.
How to go from Professor Hulk to Bruce Banner? Can't. Just can't. So there's no state transition from Professor Hulk to Dr. Banner or the Hulk. That is your question, right? There's no state transition. There's no way to go back there in this particular example, which might be the case in some of your state diagrams, not necessarily for the homework. The homework, you'll generally have a scanning state. So for a little bit of a clue on the homework, you have this very different behavior. How do I want to word this? How much time do I have? So you're going to have very different behavior based on what buttons are being pressed. So each time a button is pressed, this is the way I like to approach a state diagram. Each time a button is pressed or each time any of the API methods are called, it's 1-to-1 in the homework. Every time a button is pressed, does the behavior of any button change? So as soon as I scan 1, 2, 3, enter. When I hit 1, 2, and 3, the behavior doesn't change. All the buttons do exactly the same thing for each one of those presses. But as soon as I hit enter, for for those of you who read task 3, if you didn't read task 3, you can hit enter twice in a row to rescan the previous item. Once you hit enter, the behavior of enter changes. So we want to think that's a state transition at that point. And then once we hit a number, we're going to transition back into, okay, enter no longer has that special behavior of being able to rescan the previous item. Once we hit the checkout button, we're entering the checkout process. We can't scan items anymore. Enter doesn't do anything. The number buttons don't do anything. We have very different behavior, so that tells us that's a state transition. Yeah.
I'm basically asking the same question twice, but if I if I didn't have the use car method in the state class, and I realized that I wanted it just for Dr. Banner, the best way to implement that would be to go into the state class, add the use car method, and then go and change everything.
Yep.
And all has
Yeah, so if you want to ever add a method, so say you're doing homework 2, when you're doing task 2, you're going to write in the self-checkout class, implement all your behavior. Then when you get to task 3, you're going to want to create the state class, and you decide to defer some of that behavior to the state. And so you have your state that says, okay, number, press, enter, and checkout. I want those 3 buttons to be part of the state. And then you set it up like that. If later on you say, you know what, I also want clear press to be part of the state, you would add it to your state, add it state abstract class, add it to all of your concrete states, and then defer that behavior in your self-checkout class to be able to defer to the state. And that part we can talk about next time.